The Interference Checking and Removing Assistant tool, ICERA, is designed for AOP engineers to detect and remove functional interference between base classes and aspects in aspect-oriented designs. To the best of our knowledge, it is the first tool that adopts deduction technologies to handle functional interference problems. In this video, we show how ICERA works. The telecommunication simulation system is used as an example. The class connection in the base program uses the complete method to connect the caller with the callee. The feature which forwards busy calls is implemented as an aspect call divert. We begin in designing the base program. We first draw the structure in the AO class diagram, then specify the initial predicate, then the class invariant. The functionality of the method complete in terms of design in the class functionality view. After finishing base program design, we come to design the aspect call divert. We first draw it in AO class diagram, then define its point cut in the point cut functionality tab, and finally specifying the specification of the device before on complete in the aspect functionality tab. In the Alphabet tab, we declare all the variables occurring in all the specifications in the design. Right-click the call divert aspect and select the interference checking item. The interference checking dialog pops up. ICERA shows that to ensure non-interference, there are two properties needs to be checked. We check them using the automatic proving mode. In the proof information window, ICERA reports that the proving of the first property satisfies precondition successes, while the proving of the second property hold invariant fails. The two unproved subgoals are shown. The failure of automatically proving the second property implies that there is interference occurring in this design. A further inspection is required to find out why the two subgoals cannot be proved. We need to refine the design, that is, the specification, so that the two subgoals are proved to be true, which in turn leads to the successful proof of the second property. In this way, interference is removed from the design. Here, we take the first unproved subgoal, Theorem 2.1, as the example to show the process. The subgoal Theorem 2.1 is shown in the picture. Referring to the proof obligation generation algorithm in ICERA and the theorem expansion and proof rules of PVS, we can replace variables in the subgoal with their counterpart in the specification. After the replacement, the subgoal Theorem 2.1 is recognized as the figure. To let the proof obligation be proved, the antecedent part needs to be enhanced with the condition origin does not equal to DE exclamation mark 2. It is easy to see that the variable DE exclamation mark 2 corresponds to the variable DE in the specification, where the suffix exclamation mark 2 is generated by PVS during its automatic proof process. It promotes us to add the condition origin does not equal to DE in the specification. After re-examining the specification, we find that it is the obligation of the aspect call divert to assure that origin does not equal to DE. Thus, we added the condition to the post condition of the device before on complete. For the second unproved subgoal Theorem 2.2, we can find the failure results from the same reason as that in the Theorem 2.1. So our revise for the specification also assured Theorem 2.2 can be proved. After revising the specification, we run the property checking process. ICERA automatically completes the proof and reports success, which indicates that there is no interference in the revised design. In fact, the interference that ICERA detects corresponds to the case where the caller happens to be the target of the call divert when the callee is busy as is configured in the forwarding list. The enhanced condition origin does not equal to DE prevents the call to be diverted to the caller in that case, and thus keeps the invariant of the base program. Caller does not equal to callee in any active connection. The demo ends. Thank you.